Okay, so systems are always trying to maximize entropy, right? But systems are also always trying to minimize their energy. And these two things are in competition. If all the particles of the system were able to minimize their energy, they'd all be in ground state. But if everything was in ground state, it would push entropy to 0. Okay? The probability of everything in ground state would be 1. The multiplicity would be 1. Okay? And so this is obviously not possible. Okay? So what Boltzmann distribution does starts to talk about sort of the balance of these competing interests and how to handle both the fact that we have, we're trying to maximize entropy, but we also need to minimize energy. And then chapter 9 quantifies it with the Gibbs equation. And so again, we know that unfolding the proteins is more favorable here. We're increasing multiplicity. When we put in heat, we'll get this increase in multiplicity, this increase in entropy. However, this is a much lower energy state. Okay? They're making all of these favorable non-covalent interactions when the protein folds it up. So from an energetic standpoint, it would much rather be folded into its native form. Let me see something. Okay. So Boltzmann gave entropy a statistical definition, sort of in terms of the likelihood or the probability of things being in a certain place. And of course, he said the most probable state is the one with the highest multiplicity. Okay. Boltzmann distribution describes the probability of finding the particles of a system in any one of various states, and that can mean a lot of different things. So it could be positions, okay? It could be dye positions in the beaker of water. It could be some sort of molecular arrangement. It could be a protein conformation, okay? And the one we are talking about right now is energy levels, right? So how are things going to want to distribute themselves among different energy levels? So it tells us the likelihood of, or the probability of molecules being in a particular energy level. Boltzmann distribution tells us what distribution to expect at equilibrium, okay? So the Boltzmann distribution is what things would look like if we had sufficient time and there were no net changes in macroscale properties, okay? But what you will see on your homework and on example problems that we do, I can ask you to calculate a probability for something that has not reached equilibrium, right? Those distributions just on that other slide where the molecules were, I don't even know, 1, 2, 4, 4, 1, 2. That's not what equilibrium looks like, okay? Doesn't matter. Just know that with equilibrium, things tend towards Boltzmann. Okay, but we can also have alternative distributions. So for very large numbers of molecules, it's nearly impossible to track all their states, especially both energy and position together, okay? And it's much easier to look at the probability. Here's the figure I tried to draw for you, okay? Right, so we have these discrete and quantized energy levels. The gaps between sort of a transitional or kinetic energy level are very small. A little bit of heat going in means the particles can move faster pretty easily, whereas actually rotating around bonds takes a little bit more energy. Doing any sort of like bond stretching in this water molecule is an even bigger sort of energy gap to overcome for that to happen. And exciting things into a whole new electron shell is really, really difficult. So these are drawn totally separately, sort of kinetic energy levels, potential energy levels. This is what they really look like when you sort of lay them together, okay? You have electronic shells are the bold lines, and then within them are all the different vibrational and rotational states in between. And energy total would actually be the sum of all of these things, okay? We will always simplify to just energy, okay? In this class, know that these different things go in to it, but we will have energy levels that I'm telling you go ahead and treat them as if some of this stuff is already encompassed in going from energy level 1 to 2 or 2 to 3. We're not going to distinguish each one. But real life molecules, you know, they have several different types of potential energy and kinetic energy contributing. And I know we've seen this figure before, okay, where, you know, he can go in just to changing kinetic energy, but it can also go to exciting molecules into higher potential energy levels. So given enough time, things want to tend to relax towards a Boltzmann distribution. Okay? And the Boltzmann distribution is an exponential decaying function, okay? Where the lowest energy levels are going to be the most populated, and as the energy levels get higher, there will be fewer and fewer things in them, and it's exponential decay. And again, like I said, I can still ask you to do some calculations on a distribution that looks like this. You just know that with enough time, this is where things are tending towards, okay? Trying to move towards.